Dr. K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on environmental chemistry. We are discussing about chemistry of aquatic environment. In the previous class, we discussed about what are the chemical processes responsible for the mobility of pollutants in water, and this continuation we are going to look at another important process, namely complex formation. Especially this is applicable to metal complexation and chelate formation. Metals are an important component of water. Naturally it is present, like metals like sodium, potassium, calcium, magnesium, zinc, all this iron essentially required, and it is natural component. At the same time, there is a possibility of some highly toxic industrial effluents like containing cadmium, mercury, these type of things entering into the aquatic environment as possible. So, all this naturally occurring as well as introduced anthropogenically into the aquatic system form complex with different ligands, and we will see what are the complex formation taking place in the aquatic environment. Before going to this, generally in the elements of metals can be classified into 2 or 3 types, namely type A and type B. And there are the possibility of intermediate properties between these two, type A and type B. All this, some of these properties determine the complexing ability, and accordingly it is classified into 2 types, type A metals and type B metals. And if you look at type A, this usually these metals form complex have inert gas configuration, that is the d orbital will be 0. But if you look at the type B metals, okay, usually they will have unfilled atoms here in between D10 to this one, it will be present. And usually they type A metals, as per the scientist Pearson classification, these are all considered as the hard sphere elements, whereas type B metals are soft, considered as a soft metals. Okay. And if you look at the polarizability of these elements, type A have very low polarizability, on the other hand type B have very high polarizability, and type A usually form electrostatic model complexes. Okay. The metal will be forming a compound with the electronic bond, electrostatic interaction, that is the main components for complex formation, whereas in type B mostly it is covalent bond formation with a metal, and the ligands it is going to form complex in the aquatic environment. Some of the environmentally important metal cations are sodium, potassium, magnesium, calcium, aluminum, iron, etc. And these are all mostly naturally present in the aquatic environment. And if you consider type B metals, some examples are silver ion, lead 2 plus, mercury 2 plus, zinc 2 plus, etc. These are the elements belonging to type B. Mostly these are all toxic in nature, and some elements possess properties between these two, and it is a kind of a borderline metal ions, that is transition between type A and type B metals belong to this category. Some example include Mn2 plus, ferric, copper 2 plus, cobalt, nickel. Mostly transition metals comes into this category of borderline, that is in between type A and type B metal. And if you look at some of the properties of type metal complex formation and its ability to look at it, the complex formation of type A metals with water in a quartic system are more stable than with nitrogen or carbon as a ligand, ammonia or cyanide for example. Here water is a ligand, and we see this in comparison with the nitrogen or the carbon, relatively these type A metal will form complex, more stable complex with the water as a ligand. And other things, complexes with chloride, bromide, iodide tend to be usually weak. Okay. Usually they form univariant ligand type of complex, single one. And the metal ion may form insoluble compounds with hydroxide, carbonate, phosphate, etc. Okay. And this property also very useful in determining how the metals, suppose these metals type A metals are present and they encountered with these type of ligands like hydroxide, carbonate, phosphate, they will form insoluble compound. In fact, this property is utilized for the removal of these species. For example, if you want to remove calcium, it can be precipitated as a calcium carbonate. That is what happening in water treatment, water softening, it is possible. Similarly, a phosphate is a problem, and phosphate can be removed either complexing with insoluble compounds of calcium phosphate or aluminum phosphate. In fact, as I told you before, the halogen series, if you consider complexes with the type A metal is weak. In fact, it forms more strong complex with the fluoride compared to iodide. Aluminum fluoride is one of the important things, or calcium fluoride. These are all utilized for in water treatment. This property calcium, aluminum, they will form insoluble compounds with the calcium fluoride, aluminum fluoride. In fact, they are all utilized for this. Wherever insoluble or complex formation tendency is favored, this is utilized in their treatment. Coming to the type B metals, if you look at that, they form more stable complexes than do with the type A. If complex is formed, they form more stable complexes. And complex stability with the halide ion, especially if you look at it, iodide form much more strong complex than bromide, chloride, it is decreasing in this order. In fact, there is no fluoride complex of this type B metal, whereas type A they will form better complex with the fluoride, whereas here type B metal with more with iodide. And complex with nitrogen ligand are more stable than oxygen containing ligands. For example, type B metal form more ammonia complex or cyanide as a complex, and form stable and insoluble compounds with sulphide. Type B metal, because of the soft interaction, they form insoluble compounds with any sulfur containing ligand or sulphide as an insoluble precipitate. For example, mercury sulphide, cadmium sulphide, these are all precipitated as insoluble sulphide. And another special property of these type metal is they form organometallic compounds, that is carbon containing, organic carbon containing compounds are formed with the type B metals. For example, mercury, monomethyl mercury, dimethyl mercury, all this. Similarly, organometallic compounds of other type B metals also very important in this. And high electronegativity of metal and low electronegativity of the ligand donor atom gives a much more stable complex of this type B metal series. For example, zinc 1, mercury 1.9 electronegativity values form stable compound with the sulfur as a ligand, not with the fluoride, because fluoride is a more electronegativity element. So, that is the actually based on ability of the particular metal ion to accept electron from the ligand atoms. So, that is determining. So, chloride when compared to fluoride, iodine forms a much more stable complex with zinc, mercury, etc. Usually, the metal complex in the aquatic environment, they form complex with a different type of thing, depending on the type A or type B or intermediate, they will form specific compounds. And these metal may be present as ions or complex compound, especially with the water. Water itself can act as a ligand, either hydroxide or simple water molecule. Water hydration also is important. And inorganic ligands like chloride, carbonate, sulfate, phosphate also possible. And also organic compounds like citrate, fulvic acid, EDTA, etc., ethylene diamine tetraacetic acid. These type of compounds also favored with metal ion. It depends on what is the type of metal ions. Usually, the complex stability are explained based on what is called formation constant or overall formation constant, etc. Okay. In fact, the formation constant of this metal ion complex is very high, that indicates it forms a stable complex, and the complex formation is also very highly feasible. The higher the values of this equilibrium constant for this formation of this one actually determines high is the value, the stability as well as ease of formation is high. You just consider this: a metal ion reacts with a ligand, form a simple ligand with the Ml as a 1, with the concentration of Ml divided by metal ion concentration into L value. This is normally known as formation constant 1, only one ligand. Suppose if 4 ligands like this are reacting simultaneously and forms a Ml4, this can be represented by this Kf4, formation constant 4, that is Ml4 divided by Ml3 is a compound into its concentration L of the ligand, and this also can be represented by overall formation constant Ml4 divided by M into L power 4. So, the complex formation constant values is one of the important thing. This value tells you whether the complex formation is feasible and stable. We can get idea from this values. So, now we will see in a pure aquatic system how the metal ions form complex. The aquatic system, let us assume only water is there. So, the possibilities are either hydroxide or water alone can coordinate metal ion and form complex. So, metal ions in water are bonded or coordinated to water molecule, forms compounds, and usually such as hydrated metal ion like this M, but the water as a ligand, maybe 1 molecule, 2 molecules of water, or 5 or 6 molecules usually join to form tetrahedral or octahedral type of complexes, and they are present, or other strong bases like electron donor partner that might be present in the water system. So, they form complex. Usually, the hydrated metal ions act as an acid, especially this property is very high when the oxidation state, that is charge on the particular metal ion, is very high. That means that particular metal to form acid is very high. The hydrated metal ion will act as an acid. Bronsted acid concept, that is, they tend to lose proton in aqueous system, and usually monovalent metal ion and divalent metal ion, they do not have this property to form acid. That is, divalent metal ions do not lose a hydrogen atom at pH values usually below 6, whereas monovalent cations such as sodium ion do not act as acids and exist in water solution as simple hydrate ion. So, monovalent sodium, potassium, they never lose proton, whereas divalent usually is not normal circumstances, it is not happening. The acidity of metal ion increases with the charge and decreases with the increasing radius, ionic radius of the particular metal ion, and usually hydrated ion 3, ion with the oxidation state 3 is a behave as a relatively strong acid due to this reaction. That is, ion 3, it forms or takes 6 water molecule and form this one, and this water molecule, because of the charge to size ratio is high, that means they will lose the proton very much and behave as a strong acid like this as per this equation. That is, one of the water molecule will lose proton here as shown in this equation, and the charge you can see here, it is converted to 3 plus to 2 plus, and here neutral water molecule loses one water molecule and one hydroxide here, and this is responsible for the charge reduction 2 plus here. So, this is a property of our this highly charged ion. In addition to this, they will form precipitate as well as bridging reaction is also possible. As we have seen just now, one proton. Similarly, there is a possibility of 3 protons may lose from the water molecule. 3 protons may be lost like this and forms ferric hydroxide as a insoluble compound in water. Okay. This is also we discussed during the pH diagram about the ion compounds, various compounds there. So, in the aquatic system, if the pH is above 3, and this reaction will take place predominantly. So, usually water, natural water system pH will be around 6 to 7. There definitely if any ferric is there, that will be converted to water insoluble ferric hydroxide, that ultimately settle at the bottom of the sediment of the wherever it is there, either it is a river or surface water, whatever it is. This reaction leads to the sediment formation, and the sediment will contain ferric hydroxide. At the same time, ion may undergo dimerization or a bridging type of reaction. 2 molecules of this compound may lose water molecule and bridge 2 molecules of ion may be bridged together. So, this type of bridging reaction is also taking place in the aquatic environment. So, these type of reactions are taking place. So, sediment and suspended particle are important components of the trace metal, as we have discussed iron, and not only this, other metals like chromium, cadmium, copper, molybdenum, nickel, cobalt and manganese may be adsorbed onto this one and may be present, especially manganese and iron is one of the very important component of sediment, and these metal ions further adsorbed onto this, that is also possible. Also, these metal may be present as a discrete compounds. Ions are held by cation exchange clay. Clay minerals are present, they possess cation exchange property, and that will exchange whatever the original cations present in sodium, potassium, they may be exchanged with these type of reactions, metal ions also, that is also possible, and especially bound to hydrated oxides of iron and manganese, that is a very, very important reactions in the aquatic environment. And also chelate formation with insoluble humic substances, humic acid, fulvic acid, humus matter, etc., they also may interact with these metal ions and form complex, and that is also there. As we discussed before during the pH diagram, iron and other metals depend upon the P value and pH value, they occurs in different soluble state or insoluble state. And also some of the metalloids elements on the borderline between metal and non-metal category are significant water pollutants. For example, arsenic, selenium and antimony are of particular interest in this material series, especially if we consider arsenic or any elements with a higher oxidation state, usually they will be present as a oxyanion. More the oxidation state or valency of the particular element, like arsenic 5 or 3, similarly phosphorus, all this, molybdenum, chromium 6, everything whatever anions will be present as a oxyanions in aquatic environment, like arsenate, chromate, etc., are example for this type of things. And also not only precipitation, solubilization of metals from sedimentary or suspended matter is also possible, that actually a function of complexing agent present in this one. Okay. Certain metals whatever deposited into the sediment under favorable conditions, they may be leached out through complex formation. For example, iron, suppose it occurs in the sediment as an insoluble hydroxide, and there is a possibility of like citric acid or hydroxide or COH containing oxalic acid. These are all, they form water soluble compound leached out. In fact, oxalic acid, one of the material used to remove rust in the fabric. Any rust is there, that is iron oxide or iron hydroxide. If you rub it with the oxalic acid, it forms complex with the oxalic acid and becomes water soluble. So, this is one of the easy way of removing rust on the fabric. And similar being, any iron compound or some other metal, depending on the nature, they form water soluble compounds and leached out. So, these include amino acids such as histidine, triazine, cysteine, and citrate. Especially this is one of the thing, many industries they use a citrate also, all these compounds, and they form water soluble compound leached out. And the seawater, chloride is again one of the important complex formation, seawater. So, mercury mostly occurs in water as a tetrachloride mercurate ion, anion. Suspended particles containing trace elements may be in the sub-micrometer particle size, that also will be present in the water system. Also less available than metal ion in true solution, metals held by very small particles are more accessible than those with in the sediment. And polluted waters that is containing metal, where industrial sources like electroplating and other mining, all this, where metal ions are released into the aquatic environment in a huge quantity, add to the metal content of the stream and causing metal pollution. Okay. So, electroplating industry or metal battery operation and mining industry, all this, they contribute significant amount of metals into the aquatic system. In this, heavy metals are very, very important from environmental angle. Most of these heavy metals are highly toxic and harmful. The most harmful of the elemental pollutants and are of particular concern because of their very high toxicity to humans. In general, the transition metals and some of the representative elements such as lead and mercury in the periodic table, in the lower right hand of the corner of the periodic table also, many metals comes into this. About 16 elements are considered as a heavy metal. Usually these heavy metals possess very high density above 5, atomic number more than 20, and these elements possess toxic, they are all collectively called heavy metals. Okay. And of course, this heavy metal includes some non-metals like arsenic also. Arsenic is a non-metal or metalloid, and that is also considered as heavy metal because of this toxicity. And there is an exemption that density above 5, aluminum is the one which has density below 5 because of the neurotoxic nature of aluminum. Aluminum is also considered as a heavy metal. So, heavy metal include essential elements like iron also, as well as toxic metal as like cadmium and mercury. The term heavy metal was given because of this high toxicity of lead and mercury, which are all having density, very high density, and because of the two elements originally lead and mercury, the term heavy metals was given, and now it includes about 16 elements including arsenic and aluminum, iron. And most of these heavy metals have tremendous affinity for sulfur containing ligands or sulfur containing enzymes in the living system. They disturb the enzyme function by forming bonds with the sulfur containing groups in the enzyme presence of living things, including human beings. So, protein carboxylic acid containing COH group or amino group are also chemically bound by heavy metals. Cadmium, metals like cadmium, copper, lead and mercury ions bind to cell membranes, hindering transport process through the cell membrane of the cell wall of this living thing. And heavy metal may also precipitate phosphate, that is a biocomponent available in our system, or catalyze their decomposition. So, through all these means, the heavy metal interact and causes a toxic effect to the living things. So, in this, these metal and heavy metal interact with the organic ligands also and forms complex. One is purely complex formation with a chelate ligands are possible better, or it forms organometallic compounds, especially as I told you before, type B metals. So, there are two ways these metals forms compounds. One is through complex formation or through organometallic compounds. So, out of this, the first one is a complexation usually involving chelate. When organic ligands are involved, a reasonable definition of complex is by organic, that is applicable to natural water and wastewater system. It's a system in which special species are present that reversibly dissociate to form metal ion, and an organic complexing species as a function of hydrogen ion concentration. So, as per this equation, the metal ligand with the acid, they will remove this and forms metal 2 plus, and the ligand will take up this proton. So, in this equation, the metal ion M2 plus is a metal ion, and H2L is a acidic form of the complexing agent. Frequently, chelating ligand, that is, the chelating means it binds the organic ligands more than one site, it forms complex. I will explain what is this little later. That is, a ligand will have multi-dentate that will form compounds here. The other type of compound is organometallic compounds, and here it contains metal bound to organic entities by way of carbon atom and do not dissociate reversibly at lower pH or greater dilution, whereas here this is possible, and here the complex will not break into the reverse reaction is difficult here in the purely organometallic compounds. So, the complex formation naturally occurring chelate agents like humic acid and amino acids are found in natural water and soil, mostly coming from decomposition of vegetable matter. So, the abundance of chloride in seawater is the one gives rise to formation of chlorocomplex tetrachloromercurate, mercury with the 4 chloride ligand. This is one of the very important stable species of mercury in seawater. So, chelating ligand complex formation is a very important one. That is, the chelating means forms a ring type of structure with the metal ion, and there are many ligands used in industries, they form this, like sodium tripolyphosphate, sodium ethylene tetramine diamine tetraacetate EDTA, the popular compound. The structure is given here, and it also forms a chelate ligand, and sodium nitrotriacetate, another popular ligand, and sodium citrate. These are all compounds usually present, and example is shown here. This is a structure of nitrotriacetic acid, and how this metal ion forms a chelate ligand with a multifunctional group of this chelating agent. Both oxygen, nitrogen, all these things are involved in the complex formation, and certain organic groups which are all derived from natural thing is with a carboxylic acid or aliphatic aromatic amino group, OH group, that is phenolic, and phosphate group also form, and some of the metal ions naturally occurring and artificially introduced system all will form complex, both present in natural water as well as in biological. So, to summarize, this complex formation in water is a very important one, both naturally occurring metal ions as well as artificially introduced into the system like mercury, cadmium. All these metal ions form complex depending on soft nature or hard nature, they form complex, and the complex formation determines the solubility as well as insolubility or precipitation in this, and the mobility is determined for this important elements and the heavy